Hello, this is the section 4.2 lesson. Chapter 4 is all about probability. Probability forms the foundation of the theory for much of what we're going to do the rest of the semester. We could spend semesters studying probability. We're not going to get that in depth into probability though. We're just going to cover some of the basic concepts and ideas and familiarize ourselves with them. In this section 4.2 we're going to define some basic terms and do some simple calculations. So first let's start off with a definition. A procedure is an activity in which the result is unknown until it is performed. It's also called an experiment. An example of a procedure would be like flipping a coin. We don't know if we're going to get heads or tails until we actually flip it. Another procedure would be like taking a test. I don't know exactly what I'm going to get on the test until I actually do it. In fact, just about everything in life could be considered a procedure because you don't know exactly what you're going to get until you actually do it. Second definition, an outcome is a result of a procedure. So if I flip a coin, a result could be a heads or it could be tails. A sample space is the set of all possible outcomes. And then an event is a collection of outcomes. So as an example, let's say we flip a coin. Our sample space would be either heads or tails, because those are the two possible outcomes when I flip a coin. Let's say another procedure is that I flip a coin 3 times. Now that's not 3 separate procedures, that's one big procedure. An outcome would be the outcome I get tails, heads, tails. Another outcome could be tails, tails, tails. Another outcome could be tails, tails, heads. There are a lot of different outcomes. An event we can describe in several ways. We could describe it in words or as a list of outcomes. So as an example of an event, we could get 1 tail and 2 heads. That's a description in words. A description in terms of the outcomes would be the outcome tails, heads, heads, or heads, heads, tails, or heads, tails, heads. See that in all 3 of those outcomes we get exactly 1 tail and 2 heads. So the collection of those 3 outcomes would constitute this event. So then probability, let A be an event. The probability of A is a measure of how likely A is to occur. Now this is not at all a rigorous mathematical definition. This is a very conceptual definition. Probabilities take values between 0 and 1. Probability of 0 means that that event is impossible. A probability of 1 means that that event is certain to occur. A probability of 0.5 means there's a 50-50 chance that it will occur. If it's close to 1, we say it's likely. If it's close to 0, we say that it's unlikely. Unusual event. This is a concept that's going to come up frequently, especially later in the semester. An event A is considered unusual if the probability of A is less than 0.05. Now I warned you earlier that we're going to see this number 0.05 come up frequently. There's nothing magical about this number 0.05. It's just a number that's used frequently. Some people would consider unusual if it's less than 0.01. Some people may go as small as 0.01. A lot of different values for considered unusual, but 0.05 is the most common one. So let's talk about some different ways of calculating probabilities. Rule 1 is what we call a relative frequency approximation. And the idea here is that we perform the procedure several times and record the number of times that the event occurs. Then the probability of A is approximately equal to the number of times the event occurred divided by the number of trials. Now I'll talk about why this is an approximation here in a minute. Some other books may describe this as you take the number of successes divided by the number of trials. A success just means that we observed event A. Okay. So suppose we flip a coin 50 times and get 23 tails. So here our procedure is we flip a coin, and so we're going to repeat this several times, in this case 50 times, and I observed the event of tails 23 times. So according to my rule 1, the probability of tails is approximately 23 divided by 50, which is 0.46. But now let's suppose we flip the coin another 50 times but this time we get 29 tails. There's no guarantee that I'm going to get the same number of tails each time that I flip the coin 50 times. So in this case, the probability of tails would be 29 divided by 50, which is 0.58. So you see that in these two cases, we got different values of the probability. That's why Rule 1 only gives us an approximation of the probability. Notice that these two approximations are relatively close to each other, but they're not identical. So the fact that we got 23 tails on the first 50 flips and 29 tails on the second 50 flips illustrates what we call sampling variability, which simply means that what we get in one set of trials, which we call a sample, may be slightly different than what we get in another set. When dealing with random events or procedures like flipping a coin, you don't know exactly what you're going to get. So it means that every time you do it, you may get something a little bit different. Now, sampling variability is important because it affects our estimate of the probability. What we got in one set of 50 flips get a little different than we got in a second 50 flips, so we get different estimates of the probability. Rule 2 is a more theoretical approach. It does not require us to repeat the procedure at all. It's based purely on theory. So it will give us an exact value of the probability, but we can only apply this rule if the outcomes are all equally likely. If they are not equally likely, then we cannot apply this rule. So if they are equally likely, then the probability of A is the number of ways that it can occur divided by the size of the sample space. And this is what the book calls the actual probability, or sometimes I'll refer to it as the theoretical probability. So as an example, let's go back to our basic example of flipping a coin. My sample space consists of two outcomes, heads and tails. Each one of those two events is equally likely, so I can apply Rule 2. By Rule 2, the probability of getting a tail would be 1 divided by 2. Divide by 2 because we have two events or two outcomes in our sample space. The numerator is 1 because there's only one way that I can get a tail. So probability of a tail is 1/2. Okay. Now let's talk about what this means and what it does not mean. This does not mean that every other flip will be a tail, nor does it mean that exactly half the flips will be a tail. Those are probably two things you've observed in your own experiences. Okay. What this does mean is that if we flip a coin many times, then take the number of tails divided by the number of flips, it should be approximately 1/2. Okay. So in general, a probability of tail equals 1/2 does not tell us what will happen on a single flip of a coin. Likewise, any probability does not tell us what will happen on one instance of the procedure. It does tell us, however, what will happen on average after many flips. If we flip it many times, take the number of tails divided by the number of flips, it should be approximately 1/2. Okay. So here's an important quote to remember. A probability is an average in the long run. Again, a probability doesn't tell us what will happen on any one instance of the procedure. It just tells us what will happen in the long run. Okay, let's look at an example of using Rule 2 to calculate probabilities. Let's suppose we have a procedure that a couple has 2 children and we're interested in the genders of those children. So here on the table on the left, we've listed the sample space. We have the gender of the first child and then the second child. So we could have boy boy, boy girl, girl boy, or girl girl. So that's our sample space. Notice that we have 4 different outcomes in our sample space. And also we'll assume that all of those outcomes are equally likely. That's a reasonable assumption. That assumption is important because that means we can apply Rule 2 to calculate probabilities. So for instance, the probability that we have exactly 2 boys would be 1/4 because we have 4 outcomes, and in exactly one of those outcomes we have 2 boys. The probability that we have 1 girl would be 2/4, which is equal to 1/2. The numerator there is 2 because in 2 of those outcomes I have 1 girl. I could have boy girl or girl boy. So 2 outcomes which have 1 girl divided by 4 size of my sample space is 1/2. Probability that I have at least one boy is 3/4. That's because in 3 of those outcomes I have at least one boy. In the first one I have 2 boys, which is at least 1. Second one I have exactly 1. In the third one I have exactly 1. In the last one I don't have any boys. Now, the law of large numbers is a concept that you may have heard of before. Law of large numbers is going to relate a Rule 1 approximation to the Rule 2 theoretical value. Law of large numbers says that as the number of trials gets larger, the Rule 1 approximation of the probability of A gets closer to the actual probability from Rule 2. Say it another way, if I want a better estimate of my probability, I need to repeat my procedure more and more times. 50 times is good, 500 is better, 5,000 is even better still. The more trials, the better my estimate of the probability. Okay. So as an example, in the first couple of examples, we flipped a coin 50 times and got 23 tails. We flipped it another 50 times and got 29 tails. Well, let's combine these two results. So let's say we have one big trial with 100 flips, and we would have a total of 52 tails, 23 plus 29, so we get our 50 tails. So combining the result, the probability of a tail would be 52 divided by 100, which as a decimal is 0.52. Now notice that that's closer to 1/2 than in either one of those two instances before. So again, with more flips, meaning more trials, we get a better estimate of our probability. That's what the law of large numbers says. Rule 3 for calculating probabilities is what we call a subjective approach. And that's where we simply estimate the probability by using knowledge of the relevant circumstances. We don't use any theory. We don't repeat the procedure and over again. We just use our own knowledge to estimate the probability. So the example that we always use deals with weather. Like on the weather report, you see a probability or a chance of rain tomorrow, and it may say 30% or 80% or 50%. How did they calculate it? Well, in this case, our sample space is either rain or no rain, because it's either going to rain tomorrow or it's not going to rain tomorrow. Now, we might be tempted to say that the probability of rain tomorrow is 1/2, because we have 2 outcomes, and exactly one of those it rains, so the probability is 1/2. However, we can't use Rule 2 to calculate a probability, since these 2 outcomes are not equally likely, and it's not reasonable to assume that they are equally likely. So Rule 2 doesn't apply. Nor can we use Rule 1. We can't repeat the procedure of the weather tomorrow over and over again and count the number of times that it rains, divide that number by the number of trials. That just doesn't work. So instead we use knowledge of weather to estimate the probability. So we look at the radar and we see that there's a rain system moving in, or maybe it's moving away from us, or whatever the case may be. But they just use knowledge of weather and their available tools to estimate that probability. Last concept we're going to talk about here is the complement. The complement of an event A, denoted A bar, consists of all outcomes in which event A does not occur. So a complement is an event. It's like the opposite of the original event. So suppose our procedure is that we have 3 children. Let A be the event that we have at least one boy. A complement would be the opposite of at least one boy, which is the event that we have no boys. Or stated another way, it's the event that we get exactly 3 girls. Okay. Another procedure, suppose we guess an answer on a test. Let's let A be the event that we get the right answer, and A complement be the event that we get the wrong answer. A complement again is the opposite of the original event. Now here's a couple of equations that relate the probability of an event to the probability of its complement. The first one says the probability of the complement equals 1 minus the probability of the event. The second one is algebraically equivalent to the first one. It says the probability of the event is 1 minus the probability of the complement. Now the second one is useful because sometimes we want to calculate the probability of an event, but that's complicated. It may be easier to calculate the probability of the complement and then plug it into this second formula to get the probability of the event. So as an example of using these formulas, suppose on a multiple choice question has 4 options, one of which is correct and we guess the right answer. So the probability that I get the right answer would be 1/4. Here we use a rule 2. We have 4 outcomes. Exactly one of them is the correct answer, and we'll assume that all of those are equally likely. So we have a probability of right answer is 1/4. Now the probability of the wrong answer, there's a couple of ways that we could calculate this. Again, the wrong answer is the complement of the right answer. So it's the probability of the wrong answer is 1 minus the probability of the right answer, which is 1 minus 1/4, which is 3/4. We could have also calculated this directly from rule 2, because if I have 4 options, one of which is correct, that means 3 of them are incorrect. Take 3 divided by my sample space of 4, I get 3/4. Okay, so that's it for the section 4.2 lesson. The Course Compass homework is titled section 4.2.